All right. So we have two plan, a kind of rough sketch, and this is pretty much the level that you're going to find on the exam. That's why we do it like this. Two rough sketch plan details, wall plan details. What we're starting with is we're doing a hospital project in the southeastern U.S. under CM as constructor project delivery, and it's moved past the CD stage. So we're like, there's no bidding in CM as constructor, probably, unless there has to be because the owner rejects the CM's price. But we're pretty far along, and so design's already kind of been done. And because of an abrupt drop in the commodity price of steel, because of course the price of steel fluctuates wildly up and down, the construction manager and owner are considering meeting their budget with an exterior wall design switch from a poured-in-place concrete frame with metal panels. So here we have a poured-in-place concrete column. We have interior finish, probably gypsum board. We have steel studs, kind of cold rolled studs that are not structural, but are there to help support other secondary structure for the skin. Then we have exterior rated gypsum board right here. That's generally how we do big buildings that need a skin over a skeleton. And then we have the water resistant barrier. So this is the air, vapor, rain control layer. I can imagine it. Well, we'll talk a little bit about that in a little bit. And then we have mineral wool, which is a fibrous material, kind of like glass fiber, but its big difference is it can handle moisture. It can get wet and it's okay. Then we have metal panels on the outside, and we're going to switch to something that may be cheaper, but really late in the game. So we're going to switch to a steel. Again, here's the wide flange, which we used to call I-beams before we knew that they were called wide flanges. And then it's got spray-on fireproofing because it's also how we do steel typically. And then in this case, the interior gypsum board frames it out. Then again, we have the secondary structure that's going to hold our skin up, the cold rolled steel, lightweight gauge studs. And then we have our water resistant barrier. Again, it's going to be our air, rain, vapor control layer. Then we have EPS, and you see these little dimples. This is like a ribbed EPS. So EPS is styrofoam, it's rigid insulation, and it's got ribs there. So it's what we call drained EFIS. Exterior insulation finish system is EFIS. And it's essentially what you called stucco before you were an architect. And so it's an inexpensive, not super durable, but totally, from a building science point of view, acceptable and very inexpensive way to skin our building. So this hospital is in the southeastern U.S. So we're replacing the concrete with metal panels, left side plan detail, to a steel structure with stucco finish, right side plan detail. The soil has unusually low load bearing capacity, and hospitals, including this one, are often run with high interior humidities. They actually don't need to be, but they often are, just because they always were. So people still do it. For which of the following should the architect be most concerned related to the proposed late stage design change? And your choices are damage from a hurricane, which is the correct answer. You're going to see that in a minute. I think I accidentally showed that to you while we were waiting. A foundation unable to support the new dead loads. Moisture condensation within the walls, or thermal bridging. And so our answer is damage from a hurricane. It's not foundation unable to support the new dead loads. We'll look at the foundation in a minute, but the foundation, there's no way that the steel is going to be heavier than the concrete. And it seems unlikely that the very thin coat of stucco is going to be lighter than the metal panels, or that the EPS, which is styrofoam, is going to be lighter than the mineral wool. So at the foundation level, dead loads are really not going to be a factor. Moisture condensation within the walls and thermal bridging is not going to be a factor either, because in both cases we have exterior insulation. So there's not a real thermal bridging fear in either case. We have pretty much the same skin in both cases, more or less from a thermal point of view. Of course, the mineral wool is skinnier, but that still doesn't affect the thermal bridging. That may be a less R value, but there's no thermal bridging going across either one. So we're starting with a concept like this. where we have essentially sticks of concrete, and those are gonna be kind of composite actioned into plates of concrete. And what's really going to happen is the two are kind of going to become one in a way. And you see, sometimes we'll have a drop panel or some dropped area, like you see right here, where the column before it meets the plate, there's some extra concrete kind of beefiness, and that's going to allow those columns to engage the slab above. Now, sometimes there's not that. Typically in residential, we don't need it because the loads aren't that high, but we need it in some other applications. So just this idea of kind of a bunch of sticks and a bunch of plates, but it has the advantage that even for tall, slender things like this, if there's a force coming from, say, a hurricane or a force coming from an earthquake, so you have a lateral force, it has the advantage where if it's coming from let me see if I can. The rebar in here is actually engaging with the rebar in the slabs. The rebar in the columns and the rebar in the slabs are each kind of often turning into one another. And it's creating something that's, from a lateral point of view, if the wind's coming from the left, it's going to be stiffer than maybe it looks. It's going to be stiffer than it looks because of that composite action. It doesn't want to just kind of fold down like a house of cards, or like a basswood stick model might fold if you just had a grid of basswood sticks and you push from one side. Now, outside of that is going to be this weather resistive barrier. That's this fluid applied stuff. It could be peel and stick. It could be fluid applied. And then there's this mineral wool. That's this stuff right here. It's, again, fibrous insulation, but interestingly, because it's fibrous, it can be the drainage plane. So in other words, as moisture does get through this first layer of the metal panel, it can work its way down through the fibrous insulation, and it doesn't ruin the fibrous insulation. That's the beauty of mineral wool. I mentioned that the rebar goes beyond the column, or there's a drop panel that allows for a little bit of a beefier connection, almost like a moment connection in steel, or both. Now, for the one we're switching it to, we have steel columns, and then outside of that, we have, again, the cold rolled steel secondary structure, non-load bearing metal studs, and then outboard of that we have exterior rated gypsum board, and I've covered that in a million other 40 minutes of competence, but this is done all the time now. Some version of one of these two is done all the time, and then so this is the outside of that. So you have the cold rolled steel studs, lightweight gauge, secondary structure, and then you have the exterior rated gypsum board, which can be outside for long periods of time, not forever. But for long periods of time during construction, and it kind of maybe blows us away in terms of what we thought about. But then on top of that, again, is this fluid applied thing that, and then outside of that is going to be ribbed insulation. In this case, it's masonry, but in our case, it's going to be ephes or stucco, and so it's going to look like this. Here we have the purple exterior rated gypsum board and the weather resistive barrier, the fluid applied weather resistive barrier. And then eventually I just took this day before yesterday. Eventually it's going to kind of be all sealed in like this. And so you're essentially going to be thinking of your building as this kind of plastic encased thing, the way we would think of shrink wrap meat. That's kind of how you think of your building. That layer has to be perfect in the same way that shrink wrap has to be perfect. It doesn't really work to shrink wrap it if there's a tear in it, for instance, or if you shrink wrap your boat, if you happen to have a really nice boat, or if you dip your ice cream cone soft serve into the magic shell. It's that kind of thing. I think the best way to think of it is the bed liner in a truck. So there's in this case, again, a fluid applied thing that's put on there, and it kind of hardens and it protects the truck, and it makes the whole thing waterproof. So unless it's punctured, you've protected the metal underneath of it. So as I mentioned, the idea that our foundation somehow needs to be beefier in our building just because we've replaced concrete with steel and swapped one lightweight insulation for another, and metal panels, which are obviously heavier than this really thin layer of stucco. That's the knock on EFIS, is the layer of stucco is so thin that if you kind of rub against it with your key, don't do this, but if you next time you go to a crappy EFIS shopping center, know that if your keys were in your hand and you were to kind of rub along it, it probably would just pull the stucco right off. It's really thin. And so, and it's like I mentioned, there's a kind of a spacer behind it. So, well, let's talk about the mineral wool. So it's mineral wool metal panel. And this is how it's often done in the field. So I assume it's a better way to do it, where you have, again, the mineral wool for the moisture to go down. So we're not really worried about condensation because they're both kind of doing the same thing. They both have a drainage plane. They both have exterior insulation that's keeping the weather resistant barrier warm. So it's less likely to have condensation on it. Again, there have been lots of other 40 minutes of competence sessions that have covered that particular concept. So I invite you to take a look at those with links in our course practice exam answer explanations all throughout, especially PPD and PDD. There are explanations of this concept. It would be its own whole thing just to talk about condensation in the wall. But this is what that mineral wool looks like. So it's kind of like a more dense version of glass fiber or fiberglass insulation, and it's mineral wool, so it's wool made from minerals. So it's kind of almost like a steel wool, almost like you wash your dishes with or something. I don't know. It's hard to describe. But if you ever get a chance to squeeze it, if you squeeze it, you'll kind of understand. Like, yeah, I could see how this stuff could get wet, and I could see how it would let water go through. Now, the EPS is this. It's essentially styrofoam, rigid insulation, and then on top of that, a thin layer of stucco, and it looks something like this. And it got a bad rap in the 80s and early 90s because they often would use this, especially in humid climates, without any way to drain it. So, and this is again the subject of at least two other 40 minutes of competence. And I'm not going to get too far into it, but basically, if you have it drained EFIS like this instead of face sealed EFIS, which is when you don't have these ribs. If you have drained EFIS, then as the moisture goes through, because it will go through, it always gets through everything. As it gets through the exterior stucco and through the seams in the styrofoam in the EPS, exterior polystyrene, it gets back there and then it hits these ribs, and that keeps the polystyrene off the face of the weather-resistant barrier. Isn't it cool that you understand what I'm saying? If you've been doing this for a while, it's pretty cool that this stuff, which seemed kind of hard before, maybe to you, is now not that hard. But anyhow, if you've been doing this for a while, and then the water is going to go down and there's going to be a little way for it to get out in the bottom. Now, that is an issue. Sometimes the way out in the bottom is really not as clear as we'd want it to be. So you'll definitely want to check on that in your projects. But the idea is, again, there's sometimes the styrofoam itself is fluted. So there's like little cavities behind it that allow it to go down. Sometimes we'll put little elements on the weather resistant barrier as spacers and allow the water to drain behind the extruded polystyrene, which is behind the stucco. So what's changed then? Why are we worried about a hurricane? Well, if we have a bunch of sticks like this, the wind can come or earthquake can come from the forces from the right or the left, and the whole thing can kind of just collapse. You can't picture that, then find a way to picture it because the whole thing will just like fold because there's no rigidity on this plane, on this surface plane. And so we need to find a way to give it rigidity, and we can do that with any kind of shear wall. So shear walls can be poured in place concrete like this. At the scale of wood construction, like stick construction, you can put OSB on both sides of the stud, and that can serve as a shear wall. But you can't really do that for really big buildings. I don't think the OSB has enough lateral resistance to handle something like an earthquake. But certainly exterior rated gypsum board does not, as you might imagine, resist a big hurricane. The whole thing can still kind of just collapse. So we need to do something else. So we have really kind of three choices or some combination of three choices. We can have a core that is pretty resistive. In this case, this is a concrete block core. Now, concrete block itself is not a shear wall, but this is reinforced concrete block. So it's filled with lots of rebar and lots of grout. So it's essentially almost like a concrete wall that happens to use concrete block as kind of almost like you can think of it as a permanent formwork for the cementitious material that's inside of it. And so that will, when the hurricane or earthquake comes and forces start coming from the side, the fact that the steel is tied into the shear wall will resist it. You can see it here tied in, and you can see these big plates. I have another photo of that kind of zoomed in. And so that's why often the core of the building is built first, so the rest of it can kind of bear into it. That's one of the reasons. Also, they can get to it. But the core often is the shear wall, in no small part because the core is also often includes the shafts for the emergency stairs and the egress, and those have to be fireproofed anyway. And it's a good way to fireproof it is by making it. So again, we're going to tie the steel into the core. Provided, as you might imagine, if we have a small core and a really big building, that's not going to do the job. So there has to be a good deal of engineering that goes into it. And then here you see there's also cross bracing in this dimension. So it's not one or the other, it can be both. So the cross bracing will also, as we're going to see in a minute, the cross bracing will also do the job of making it stiff and resistive towards lateral loads. And here it is, where it's the steel is kind of these plates are bolted into the grout, and you see that if they seem like they're much more massive than they need to be, that's the reason. It's because this shaft wall has to resist all the wind loads. You see it here as well, and there, and zoom in. And then we have cross bracing, right? So like you see right here, and if we have cross bracing, then we can resist the loads. But you can imagine if we started without the need for cross bracing during design, and then we switched to steel from concrete. And remember, the concrete doesn't need cross bracing, even though it looks like it does right here. So maybe this is not the best example. But if we switch to cross bracing, when we have the whole design done, you can imagine that cross bracing is very likely to go across a couple of windows, across a couple of doors. It's just going to cause trouble. So cross bracing becomes really difficult, and that's one of the reasons. Cross bracing makes it rigid from right to left, and we're going to fire coat that as well. But cross bracing is going to make it really difficult if it wasn't there before, if we want to keep everything in the same place in our design this late in the game. And so cross bracing is often not an option. So then we're going to have a moment connection, which is happening here. So this is a shear connection or a pin connection. This is a rigid connection or a moment connection where the flange is engaged, and it's a much beefier connection. And as I've mentioned many times, it's way more expensive. And so we could easily evaporate all of our savings that we got from switching to steel if we have to pay really high skilled metal fabricators and welders lots of money to be high in the sky in bad weather, putting lots of welds and bolts to connect flanges and that kind of thing. It's amazing to me how expensive that winds up being. All right, I will open it up to questions. So go ahead and raise your hand if you want to ask a question.
Hello.
Hello.
Cool. Thanks for the presentation. So I just wanted to clarify the answer was damage due to hurricane, because Correct. You would have to pay more for a moment connection. So account for that. Right?
You would have to account for it by either changing some of your walls to shear walls or your core to shear walls so they could resist, and or putting cross bracing here and there so that it could resist, and or doing moment connections, which is probably, you're right, the most likely scenario, in which case, again, you're cost estimators and your your structural engineer has to get involved. So in other words, you look at that, you're not that worried about thermal bridging, you're not that worried about dead loads, you're not that worried about, it's basically you're picking the best answer. You as an architect are, like you can't do it. Like once they give you a change like that, you're not going to redesign the whole building. So it's like, what do you have to worry about, right? It's actually a pretty reasonable question. What as an architect you have to prioritize? And of those four choices, dead loads is not going to be because the new one's lighter. Condensations, it's not going to be because there's no reason to think there's going to be more condensation in the new design. Thermal bridging is not going to be an issue because there's no more thermal bridging in the new design. But there could be cost or significant design changes and certainly structural calculations that would need to be done everywhere once you change it to steel for lateral loads. So that's basically the answer.
Okay, because it's not just one location, right? It's like everywhere that they would put.
It's like everywhere. Moment frames are everywhere. That's why they're so expensive. They're not just one little area. They're everywhere. All right, guys. Good night. Get licensed.